Hello, and thank you for watching our presentation. My name is Jose Rodrigo Sanchez Vicarte, and I will be presenting Double Cross, Subverting Active Learning Systems. This work is done in collaboration with Wang and Christopher Fletcher, my advisor, from the University of Illinois at Urbana-Champaign. Machine learning models are increasingly used in security or safety sensitive areas, like autonomous driving, facial recognition, emergency response, and online content moderation. These models all face a common challenge: the need for a continuous supply of new labeled data for training. This is because the environments they are deployed in are usually dynamically changing. By continuing to train on newly available data, these models can adapt to dynamic environments while increasing their accuracy. This creates a strong demand for data collection. Consider a typical scenario. A user submits some unlabeled data to the deployed, trained model and receives a label in return. On the back end, the service provider collects the user's data. The true label of this data is not known by the service provider at this point. So they leverage data labeling services like Mechanical Turk to determine the true label. The data and the label can then be used to improve the model during retraining. For example, if a sample was originally misclassified, training on that sample can make the model more likely to classify similar samples correctly in the future. Continually collecting and labeling data for retraining is a key idea behind active learning. Training on submitted data, however, creates a dangerous opportunity for an adversary to pollute the training set. But it's not as straightforward as simply submitting malicious data. Ultimately, not all collected data is used for retraining. Let's understand why that is. Manual labeling is expensive, and as the number of users and submitted data increases, labeling all data quickly becomes prohibitively expensive. Active learning attempts to reduce labeling costs by reducing the amount of data to label. The output of the model is first used to algorithmically decide whether each input has high or low utility. Inputs which are considered less useful to the model are not labeled or used during retraining. Only those inputs which are considered high utility are labeled and then used for retraining. In this work, we present an end-to-end attack against active learning, which allows the adversary to pollute the training set and ultimately force the victim model to selectively classify triggered inputs to an adversarially selected target class. Furthermore, the victim model's accuracy on non-triggered inputs is not degraded, making the attack difficult to detect. However, active learning is not trivial to attack. First of all, it performs aggressive filtering of inputs. Inputs which are not deemed algorithmically useful are simply discarded. Active learning also involves human annotators during retraining. If these annotators are unable to determine the true label of an input, the input cannot be used for retraining. Adversarial modifications to inputs, for this reason, must be stealthy. In short, malicious inputs must be both algorithmically selected and manually labeled before they can be used for victim retraining. We present the double cross attack to simultaneously bypass selection and labeling. Notably, the victim model itself presents an additional challenge. The adversary is attacking a model which is only performing incremental retraining. Conventional Trojan and backdoor attacks often assume that malicious samples will be added to the training set before the victim model has even begun training. This is not the case for active learning. We present a complementary technique which allows the adversary to achieve a high success rate even after a single epoch of victim retraining. Notably, we perform our evaluations over fewer epochs of retraining than those used during original training. We demonstrate this attack on various DNNs as well as on Amazon's active learning framework, AWS SageMaker. First, we must understand how inputs are selected for labeling. A common approach for input selection is uncertainty sampling. Consider an input to a model. When the model processes the input, it outputs confidences. Confidences are a vector of probabilities that the sample belongs to any one class. That is, if the model can classify among 3 different classes, it outputs a vector of 3 probabilities. The class with the largest probability, the highest confidence, is then returned as the model's classification. Margin sampling, a form of uncertainty sampling, leverages this information to evaluate whether a sample is worth training on. If the differences, the margin, between the 2 largest confidences are small, the model is uncertain about its prediction. Samples with small margins are deemed higher utility than those with larger margins. The adversary, then, must design triggers which cause the victim model to have a small margin on malicious data. It is, however, rare for models to directly expose confidences. We therefore evaluate over two settings: a gray box setting, where confidences are exposed and can be directly optimized, and a black box setting, where only the most probable label is exposed. There are, inherently, many ways to design a trigger. We use a generator to implement a differentiable function to simultaneously optimize for both selectability and stealth. This generator first outputs a candidate trigger. We can, at this point, directly optimize the magnitude of the trigger for stealth without querying the victim. The trigger is then overlaid on a clean input of the target class. That triggered input is fed into the victim. The victim's output can then be used to optimize for selectability. To this end, we use a dual loss function for the generator. The stealthiness of the trigger is estimated by its magnitude, and the selectability of triggered samples is computed by querying the victim. We evaluate the effectiveness of our trigger generator and loss function under two scenarios, a gray box scenario and a black box one. Under the gray box setting, the victim publicly outputs confidences. This allows the adversary to directly compute and minimize the margin. Under the black box setting, the victim does not publicly output confidences. Instead, only the predicted label is output. Under this model, the adversary instead optimizes the trigger so the victim will incorrectly classify it. Intuitively, the black box approach works because the model is more likely to have a low confidence about inputs it misclassifies. Our work assumes the adversary can submit samples for evaluation without adding them to the victim's training set. This is akin to a service where users can request that their data not be collected. Once the adversary has designed a trigger which meets these two criteria, they are ready to begin submitting samples for retraining. The generator ceases training at this point, and the second stage can begin. The adversary overlays the trigger on many samples of the target class and submits them. These samples then go through the normal active learning flow. Samples which are not selectable are simply discarded, while samples which are selectable are manually labeled. Using Amazon's SageMaker service, we evaluated that labelers can correctly assign the true label. That is, this triggered input would still be assigned the label of mountain. Malicious samples, which met these two requirements, are then added to the training set and used for victim retraining. Conservatively, we do not assume that malicious samples are permanently added to the training set. That is, each malicious sample is seen only once by the victim. In order to be used across multiple epochs, the same sample would have to be selected and labeled multiple times. In the paper, we evaluate against selection criteria stricter than that used by Amazon's SageMaker. We also provide an analysis on the impact of the selection criteria. Furthermore, we validate that our triggered samples are labeled correctly by SageMaker's annotators. Finally, the adversary is ready to exploit the trigger. The adversary overlays the same trigger, which was used during retraining, on images of a different class. In this case, an image of a cat. The model, incorrectly recognizing the trigger as a feature of the mountain class, classifies the input to the adversary's target class. We develop an additional adversarial technique to boost the success rate after the victim retraining phase. In cases where the trigger does not successfully cause a misprediction, the adversary can boost the trigger intensity, sacrificing some stealth for a higher success rate. This technique allows the adversary to achieve high success rates even after a single epoch of victim retraining. We find this technique to be effective in both the gray and black box settings. The adversary initially submits samples for victim retraining with a single trigger intensity. When exploiting the trigger, the adversary submits samples with a boosted trigger intensity. Note that when the intensity of the trigger is the same across both stages, adversarial success rate can remain low. When the intensity is boosted, however, success rate can significantly increase. Notably, this is not a required technique for double-cross attacks. We demonstrate that an adversary can achieve similar results by submitting more samples for victim retraining across more retraining epochs. To evaluate our triggers, we first consider a simple baseline. We generate a trigger by starting with random noise and slowly increasing its intensity until obtaining a trigger which is consistently selectable. This trigger achieves a success rate of 86.2%, albeit with significant distortion to the data. Using a gray box approach for double cross, we design a trigger which is significantly stealthier while improving the success rate to 93.7%. Using our black box approach, we design a trigger which remains stealthy, albeit with a decrease in the success rate to 75.4%. Notably, if we were to use a random noise-based trigger that is as stealthy as the black box approach, it would only achieve a 60% success rate. Finally, I will discuss the challenges facing defenses. We found that robust training aggravates, but does not prevent, double-cross attacks. Especially in the security-sensitive scenarios previously discussed, an adversary can still cause significant damage. A detailed discussion of this defense and its limitations can be found in the paper. Detecting and filtering out malicious inputs, another proposed line of defense, is inherently at odds with active learning. Active learning attempts to find the most useful samples for retraining. These are, most likely, the same types of inputs which would be filtered out. A key challenge, therefore, remains for this line of defense: how to avoid malicious data while ensuring that the most useful data is kept. Similarly, it can be difficult to train annotators to recognize the trigger pattern, especially because the adversary intuitively can change the trigger pattern from that described in our work. In conclusion, we presented double cross, an end-to-end attack on active learning. The key novelty behind this attack is simultaneously manipulating the active learning labeling process and the target application. The attack simultaneously bypasses the active learning selection criteria and the human labeling process to insert itself into the retraining set and change the victim model's future behavior. We demonstrated this attack in both a gray box and a black box setting, as well as evaluating against Amazon SageMaker's human annotators to confirm the practicality of the attack.